you could do the same thing to parametrize a plane, or at least something similar. If you have a plane, any 3 points are going to define a plane. What you can do is you can find a vector, one vector that lies in the plane, let's call it u, and another vector that lies in the plane. So using your 3 points, you could find these 2 vectors. Those are 2 directions that lie parallel to the plane. And then to get the particular plane, you can take those directions, and we'll use 2 parameters. Let's use u times one parameter s and v times another parameter t. And then we'll just add some starting point to that. So without adding this point in, then when s and t were both 0, you'd be in the origin. So if your plane doesn't go through the origin, you've got to push it out. And this will give our parametrization as a function of 2 parameters, s and t. We expect there to be 2 freedoms, right? Because a plane is 2-dimensional. So s and t represent the 2 freedoms. So you can choose these 2 numbers, and then that will lock in, given any choice of those 2, that will lock in the particular location on the plane where you are. Let's look at that in this case. So I'm going to find 2 vectors in the plane by subtracting points. Let's see, the vector from 0, 1, 2 to -3, 2, -1 would have to lie in the plane. -3 minus 0 is -3. 2 minus 1 is 1. -1 minus 2 is -3. So there's one vector that lies in the plane. And another vector, I could go from 0, 1, 2 to 1, 1, 1. 1 minus 0 is 1, and 1 minus 1 is 0, and 1 minus 2 is -1. So there's another vector that lies parallel to the plane. So then to create our parametrization, we'll just take u times one scalar parameter and v times the other scalar parameter. Basically, we can take we're making combinations of u and v, so you can use a little bit of u and a little bit of v, and adding those together will locate you at some point in the plane, right? So depending on how much u you use and how much v you use, you'll be able to arrive at different locations, but they'll all be in the plane created by u and v, right? So let's see. I'm going to take u times s, so that's going to be -3s, 1s, and -3s, plus v times t, so that's going to be t0, -t, just multiplying t through v here. And then I need my starting point, so I'll just use that point 0, 1, 2. And put that all together, and I'll get a vector equation that has 3 entries: -3s plus t plus 0, right? And s plus 0 plus 1, so s plus 1, and -3s minus t plus 2. There's our parametrization of the plane. So if we let s, let's see, if we let s go from -infinity to infinity, and t go from -infinity to infinity, then we'll see the entire plane eventually, right? By visiting all the different possibilities for s and t, we can get to all the different points that actually lie on the plane. If we put restrictions on s, or restrictions on t, or restrictions on both, then we'll only see certain parts of the plane depending on the restrictions that we choose. Okay, so you can think of this as giving us really 3 equations, right? An x equation, a y equation, and oops, this whole thing is your z equation. Now, that way, we've written the equations of the plane as in terms of 2 parameters, 2 numbers on the side, s and t. They represent our 2 freedoms along that 3-dimensional plane, or that 2-dimensional plane in 3-dimensional space. So another way to write the equation of the plane is in terms of the vector that's perpendicular to it. Here's the picture. Suppose you've got a plane. If you know the vector that is perpendicular or normal to the plane, let me call it little n for normal. Remember, that's different than the word norm. The word norm meant the length of something, or the measure of a vector. This n means normal. Normal means perpendicular. So this is perpendicular to the plane here. So this vector is coming right out of the center of the plane. if you know the normal and you know a point on the plane, let's call it x naught, y naught, and z naught, any other point on the plane, x, y, z, if you were to find the vector that would carry you from that known point to any other point, it would have to be perpendicular to the normal. Now the vector that would carry you from x naught, y naught, z naught to x, y, z would be x minus x naught, y minus y naught, and z minus z naught. So if that's a vector that lies in the plane, if you dot it with the normal, let's say the normal has three components, a, b, and c. So if you dot that with the normal, would have to be perpendicular. So when two vectors are perpendicular, you get 0. Okay. So the book writes this as n, the normal, dotted with the vector from a given point to any other point. So they call that vector p naught p. Okay, and that has to be 0. They call this the vector equation of a plane. And then we can write this in its component form, right? In fact, we could actually do the dot product. That would be what they call the component form. X minus x naught plus b times y minus y naught. I'm just doing the dot product here. C times z minus z naught equals 0. In fact, we could, these x naught, y naught, z naught, those are going to be known constants. It's x, y, and z that are going to be the variables. So the variable stuff is going to be ax, by, and cz. The rest of these are going to be constants, ax naught, by naught, cz naught. So let's just move them all over onto the right-hand side and call them d. So if you see an equation like this, you can tell that you could go backwards and discover the normal, which would be the coefficients. It would come from the coefficients of x, y, and z, right? And then you could solve this equation to find some point x naught, y naught, z naught on the plane, and you'd know that this is the equation of some plane. You can read off the normal right there. So if you want to know the normal to a plane, just read off, if you have it in this form, in this component form, then you can just read off the normal from there. Let's do it in this particular case. So we have these 3 points. We've got to find a vector that's perpendicular to the plane. And here's our idea. Like before, we'll find 2 vectors that lie in the plane, and then to find one perpendicular, we could use the cross product. So let's again find our 2 vectors that lie in the plane. Let's see. -3 minus 0, 2 minus 1, and -1 minus 2. So there's one vector that lies in the plane. We could find another vector in the plane by taking this minus that, right? So we got 1 minus 0, 1 minus 1, and 1 minus 2. So those are the same 2 vectors that we found before when we were writing the parametric equations of the plane. Now we're working on finding the normal equations. Now to find something perpendicular, let's do the cross product. -3. 1, -3, 1, 0, -1. We're just going to take the determinant of that. We have I times -1 minus 0. We have j, it's in a negative position, and then we have 3 minus minus 3, so that's 6. So, but it's in a minus position, so we have minus 6. And then we have k times 0 minus 1. Okay, always a good idea to check your cross product before you go any further. It should be perpendicular to the 2 original vectors. That's why we're doing it, right, to get a normal. So if we check it with v here, we get -1 plus 1, that's 0. If we check it with u, we get 3 minus 6, and 3, that's 0. So we achieved our objective. We found something perpendicular to both u and v. So this is going to be the normal that we use. Then we can find the equation of the plane by dotting our normal, -1, -6, -1. With this vector, we could use any one of these points. It just has to be some point p naught in the plane. We'll just use this one, maybe. So x minus 0, y minus 1, and z minus 2. Okay, if you used one of the other 2 points that you had, it would look different at this stage, but by the time you got it into this form, it would be essentially the same thing. So if we do the dot product, -1 times x is -x, -6 times y minus 1 would be -6y plus 6, and negative 1 would give me negative z plus 2 equals 0. So the equation of the plane is, let's see, 6 and 2 are 8. We'll move them over here, and we'll have negative 8 there. Or we could multiply all the way through by negative. Since everything seems to have a negative there, it might be nicer to have x plus 6y plus z equals positive 8. You can check and make sure that each of the three components actually lie on the line. So if you put in 0, 1, and 2 for x, y, and z, you get 6 plus 2 is 8. So that works for that point. Now let's try the next point. Negative 3 plus 6 times 2 is 12, so that's 9. Minus 1 would be 8. Yeah, that one works. And then 1, 1, 1. So you'd have x plus 6 plus 1, or 1 plus 6 plus 1 is 8. Yeah, so this works. This is the normal equation of the plane. You can notice the difference between the two of these. So in the parametric equations, right, we had x, y, and z as individual functions of two parameters s and t. That's one way of representing the plane. That's a parametrization. So in the other way, we have it just as a single constraint. So we have three freedoms, x, y, and z, and one equation that has to be satisfied, and that means that we have just two freedoms left, right? We have this two-dimensional object, the plane.